If an electron is simply a charged particle moving in a circle, does that mean every atom in the universe acts like a microscopic electromagnet? To find out, we start with a foundational physical model, an atom consisting of a single negatively charged electron revolving in a stable path around a positively charged nucleus. To measure this physical system, we need to track two kinematic variables, the radius of the electron's orbit, r, and its tangential velocity, v. Classical physics dictates that any moving charge constitutes an electric current. By treating this circular orbital path as a continuous loop of wire, our objective becomes clear. We need to calculate the exact current flowing through this loop and the area it encloses. If we can quantify those two properties, we have all the data required to calculate the atom's intrinsic magnetic dipole moment. This derivation maps out the math. We define electric current for a single particle as its charge, E, divided by the time it takes to complete one full orbit, its period, t. Substituting the formula for the period of a circle gives us a current of EV divided by 2 pi r. Next, we take the standard formula for the magnetic moment of a current loop, the current multiplied by the physical area of the circle, pi r squared. By substituting our calculated current into that equation, the pi terms and one radius term cancel out. We arrive at a clean classical result. The electron's magnetic moment equals EVR divided by 2. Now, we connect this electrical property directly to the electron's physical motion. We know mechanical angular momentum, L, equals mass times velocity times radius. By multiplying and dividing our magnetic moment equation by the mass of the electron, we can isolate that MVR group and replace it entirely with the angular momentum variable, L. The conclusion here is highly specific. The magnetic strength of an orbiting electron is precisely dictated by its mechanical momentum. Looking at the center of the derivation, if we rearrange that equation, we isolate the gyromagnetic ratio. This is a fundamental constant for the electron, specifically 8.8 times 10 to the 10th coulombs per kilogram. Translating this from two-dimensional algebra to physical reality requires factors. Applying the right-hand rule to the electron's physical direction of motion, the angular momentum vector points straight up, perpendicular to the orbital plane. Here is the physical catch. Because the electron carries a negative charge, conventional current flows in the exact opposite direction of the actual particle. That reversed flow flips the magnetic moment vector, pointing it straight down. In the final green box here, we formalize this opposition. We introduce vector arrows and a mandatory negative sign, permanently locking the magnetic moment in direct opposition to the angular momentum. Before we take the final step, pause the video and try to recall Niels Bohr's specific quantization rule for angular momentum. While classical mechanics perfectly calculates this ratio and the opposite vector directions, it wrongly assumes an electron can orbit at any arbitrary radius. It fails to explain why atomic properties are fixed. For that, we require quantum mechanics. Niels Bohr resolved this continuous orbit problem with his second postulate. An electron's angular momentum is not arbitrary. It is mathematically quantized into discrete steps of an integer, n, multiplied by Planck's constant over 2 pi. Looking at this final set of calculations, we can merge the classical and quantum worlds. By substituting Bohr's exact quantization condition for L directly into our derived magnetic moment equation, we get NEH over 4 pi m. Because the mechanical momentum is locked into specific whole number steps, where n equals 1, 2, 3, and so on, the atom's magnetic capability is inherently locked into those exact same discrete steps. By setting that integer n to 1, we calculate the properties of the ground state. This defines the absolute minimum possible magnetic moment for a revolving electron. This foundational unit is known as the Bohr magneton. Plugging in the known constants for charge, mass, and Planck's constant resolves to exactly 9.27 times 10 to the negative 24 ampere square meters. By mapping the classical mechanics of a single spinning charge onto the strict boundary rules of quantum physics, we arrive at a precise physical baseline. We have quantified the lowest limit of magnetic strength, isolating the fundamental pixel of magnetism.